So our next speaker is Chenkai Yu. Chenkai is a student at the Institute for Interdisciplinary Information Sciences at Tsinghua University, working at the intersection of computer science and economics to solve emerging problems with real-world impacts in interdisciplinary research areas. He's also been a visiting student at Caltech and at the University of Michigan. And the title of the talk is Timely Information from Prediction Markets. So welcome, Chenkai.
I'm Chenkai Yu from Tsinghua University, and this is a joint work with Grants and Fang Yi. So this research is related to prediction markets, information, and social welfare. Imagine, what is the relationship between US Open ejecting spectators and a $300 million cable connecting New York City to Chicago? Both are related to prediction markets. The US Open ejected 20 spectators for court-siding and banned them from future events. Those people, called court-siders, attend sport events and send back information in real time in order to gain profits. Because sportcasts are usually delayed by a few seconds, those agents with real-time information can gain rewards by trading just seconds before others. For example, in like sports gambling markets. And as for the cable is used by high-frequency trading firms to reduce trading latency from 14 milliseconds to 13 milliseconds. They just want to be 1 millisecond quicker than others in order to arbitrage across markets. This is achieved by building a direct route from New York City to Chicago rather than using a previous longer cable that goes through Philadelphia. To make it even worse, soon after this new cable is built, people found other technologies to achieve even faster communication speed and kept investing in large amount of resources only to be milliseconds faster than other people in trading in the markets. And this seems to be obvious waste of social welfare. So our paper aims to design prediction markets with good social welfare. Let's see an example. Say 3 agents received a task to predict whether it will rain tomorrow. And the outcome random variable is binary. Okay. Say agent individually decide how much to invest in order to obtain their own information or their own signals, and what and when to report to the mechanism. The first agent, say, invest or spend $10 to buy pen and papers, and after 5 hours, she obtained her signal X1. And then she reports something to the signal at time S1. The second agent spends something more to buy better equipment. And after 3 hours, he obtained his signal X2, and then he chooses a time S2 to report something to the mechanism. And third agent spent even more to buy even better equipment. And she gets the signal in shorter time, say 2 hours. And then she reports something to the mechanism at time S3. We assume that this TI is sampled from a random variable capital TI that is depending on CI, which is how much the agent invests at the beginning. Okay. So our goal is to design mechanism to aggregate truthful and timely information to maximize social welfare. We want this mechanism to maintain a real-time belief over time. By truthful, we mean each agent performs a Bayesian update on the market belief. And by timely, we mean each agent reports as soon as they obtain their signals. This actually means SI equals to TI. Recall that agents obtain their information at time TI and reports their signals at time SI. So timeliness means SI equals to agent choose SI such that it equals to TI. So we want to maximize the social welfare, which is defined to be the expected value of the total societal value minus the total cost spent by the agent, where the societal value is defined to be the integration over time about S times H, where S is a given proper scoring rule that models how the society benefits from the market, and H of T models the principles or the mechanism designers or whatever whoever in the society that benefits from the markets, his or her value of information at time t. We have two examples here. The first one, H of t is equal to 1 if t is smaller than some deadline t star. So it means the information is valuable before a deadline and is useless after this deadline. And in example 2, we have H of t equals to a exponential function, which means the value of information decays exponentially fast with a constant rate. And now it's important to know that classic prediction markets are neither welfare optimal nor timely. And we will illustrate this in the later slides. This is the classic prediction markets. And in the beginning, there's a prior belief that is public called P0. And then the fastest agent comes and updates the public belief using her own signal X3. And the market belief becomes P sub 1. And then the second fast agent comes using his signal X2 to update the market belief to be P2. And then the slowest agent comes to update the market belief to be P3. And finally, the outcome is revealed to be Y, which is a binary variable. And then the prediction market pays each agent by some formula, where S is a proper scoring rule that can incentivize truthfulness. The theorem here is that if each agent is allowed to update only once, then prediction market is truthful, which means the agents are incentivized to do Bayesian updates using his or her signals. And as an example, we have quadratic scoring rule is defined like this, which is like 2 times P of Y minus the norm of P. Here, P is a distribution over binary outcomes. So it is a vector with 2 items. Intuitively, the closer P and Y are, the higher the score will be. Now we explain why the classic prediction market is not welfare optimal. Here are 2 numerical examples. Agents may compete to exhaust the social welfare. In the 2 examples, the outcome welfare is significantly lower than the optimal welfare, and outcome cost is significantly higher than the optimal cost. The 2 examples are called linear and exponential. We'll explain it in the next slides. The setting is like this. We can use any scoring rule S, and it is important to know that agent signals are identical to the true outcome. This means all xi are equal to y. Here, the agent signals are complete substitute to each other. So only the first report is valuable, and only the fastest reporter will be rewarded. And in this setting, because of this, agents are willing to compete with each other to be the first one. Otherwise, they will not be rewarded. And as for the time value, we use the deadline model. So information is only valuable before deadline. The 2 examples uses 2 different model of access functions, which means in the first one, the probability that an agent gets her signal before the deadline is linear in CI, which is how much she invests at the beginning of the model. And in the exponential setting, the probability of getting signals before the deadline is described by some exponential function in CI. So this is actually very easy to show. For example, in the linear setting, we just compute the maximum of the utility of each agent. We set the derivative to be 0, and after some computation, we can obtain the results that this orange equation, which basically says the social welfare is 0 in equilibrium. And moreover, the classic prediction markets do not incentivize timely reports either. This is actually discovered previously by Chen and Wagner. This right figure here shows that the reward for the case reporter is not always decreasing. In fact, it is better to be the third to report rather than the first. The specific settings like this, we use quadratic scoring rule, and the information structure is different from the previous example. Here, the prior belief of the outcome is close to one of the extremes, 0 or 1, and agents' belief are IID conditioned on the outcome y with probability 0.8 to equal to the outcome y. This phenomenon depends on the specific scoring rule. In fact, the logarithmic scoring rule can avoid this, while the quadratic scoring rule introduces this problem. The intuition that the quadratic scoring rule is more able to distinguish probabilities close to 1/2 and less able to distinguish them close to extremes, 0 or 1, compared to the logarithmic scoring rule. So when the prior is close to 1/2, the update in the market will be larger. But in this example, the prior at the beginning is close to 0. So the first few agents are getting the prior to be closer to 1/2, and then the next agent will benefit from this because they can move the market's belief larger, by a larger extent. So this is basically the intuition of this phenomenon. And finally, we have the positive results. We design mechanisms that are truthful, timely, and welfare optimal. And we have these assumptions. Some of them are already familiar and introduced in the previous slides, like how long agents get their signals depends on how much they invest at the beginning. Their signals are IID conditioned on the true outcome y. The prior of the outcome is a public information. Agents knows the relationship between their access time and how much they invest at the beginning, and they knows the conditional distribution of the signal conditioned on the outcome. However, the principal doesn't know these two information. So I mean the mechanism designer doesn't know these information. So that introduces challenges in the design of mechanisms. And I will briefly talk about the intuition of our mechanisms. The intuition is to pay each agent by the difference between actual value of information and the counterfactual value of information. Here, by counterfactual value, we mean the value as if this agent had not updated the market, rather than had not participated in the game. The agent, anyway, they invested at the beginning and just didn't change the market belief. So this is how we define counterfactual value of information. The intuition is a little similar to VCG, but VCG doesn't directly apply here. For an intuition, if the reports are late, then, I mean, late report actually pushes the blue line to the right side in terms of the time, and non-truthful report will push the blue line downward. So either of them reduces the value of the reward. Although this is a very rough intuition, and so like more technical result can be found in our paper. The intuition of our algorithm is that we try to elicit the signals from each agent, and the mechanism, instead of the agent, do sequential Bayesian updates using either all signals or all except one of them in order to compute the actual value and the counterfactual value over time. So some future directions, one of the interesting directions to consider different types of information being available starting at different times, or we may consider how to relax the conditional IID assumption on agent signals. These are some potential directions. And I think these are all of my presentation, and questions are welcome.
So again, I guess I'll start us off. I was wondering a bit about how much the mechanism needs to know, and whether it's interesting to play around with that.
How much the mechanism needs to know?
I mean, excuse me, about the signals or about the information, the distribution of information. Like, so does it need to be able to do Bayesian updating and know about priors?
Yeah, we assume the priors, the prior of Y is public information.
And also like the signals distributions, or I may have missed that.
It could be any distribution as long as they are IID conditionally IID.
Mm-hmm.
Yeah.
Thank you.
Thank you.
Questions?
I had a question. Very nice talk. Is the value of information hard to compute, or the counterfactual value of information? Are those hard to compute?
They are not very hard to compute. So as I have said, our mechanism elicits the agent signals. So the mechanism can do Bayesian updates for the agents. So using agent signals. So the actual value of information is computed by updating using all signals timely. And the counterfactual one means we leave one of the signals out and using other signals to update the belief. Does it answer your question?
Great. Yeah. Yes. Thank you.